All right, so the first one, 340 degrees, when we don't see any other indication, we're going to assume this is Cartesian, meaning the normal Cartesian plane that we are used to. And my direction, the reference starts at the positive x-axis, so it starts here. And we're going to go counterclockwise. Counterclockwise. Positive means counterclockwise. So I am going to start at my x-axis. I'm going to go counterclockwise. That's 90, 180, 270. All the way around would be 360. So I'm going to just stop short of 360. That is my 340 degree angle. My reference angle is how far away I am from the closest x-axis. So what is my reference angle for this one? It's just 20 degrees. Remember, when you're in this quadrant, you're going to take 360 minus your angle to get your reference angle. For the next one, it says that we are 47 degrees west of south. So for this one, we're going to think north, south, east, and west. And so if I want to go 47 degrees west of south, I start at south and I go west 47 degrees, which is going to be a little bit more than halfway, right? 45 would be halfway. So we're talking right there. This is my 47 degrees west of south. How far away am I from my closest x-axis? Right? So this whole quadrant is going to be 90. So I'm going to say 43 degrees is going to be my reference angle right there. 43 degrees is going to be my reference angle for that one. Right, the last one is a true position, meaning we're starting from true north. North right here. But this is always clockwise, right? Whereas the first one is always counterclockwise. Your directional, your cardinal directions, north of east, west of south, whatever, those are based on how they tell you to move. And then the true north position is always clockwise, always clockwise. So for this one, I'm going to go 157 degrees clockwise. So I'm going to start here. I'm going to go 90. And remember, all the way would be 180. So I'm going to go over here. Now, in this case, my closest x-axis is this one. I went 90 right here. How far past did I go? How far past that 90 did I go? 67. So that's how far away I am from that closest x-axis. That would be my reference angle there. The first thing we're going to talk about with calculating vectors is really just position and looking at it graphically. And so when you start seeing it graphically, then when we start throwing in word problems where you don't really have it graphically, what your brain does is it starts to think about what makes sense and what doesn't make sense when it comes to movement. So the first definition that we get to, the result of a vector sum, what happens when we add vectors, we get what's called a resultant. And so typically what you're solving for is resultant. Resultant is basically what you're looking for in a displacement type situation. Resultant is like I started here, I moved around, and I ended up here. The resultant is really what would happen if I had gone directly from one to the other instead of kind of around. All right, and so a couple of things about adding them. A couple of things about adding vectors. If the vectors have the same direction, then the resultant will have the same direction. And the magnitude's really easy to calculate. You just add them. So what we did in the last chapter is it was all one direction movement. Meaning if I started driving my car and I was going this direction, no matter what happened with acceleration or velocity, I was still going in the same direction. And so when we're talking one direction, that's really easy because you're just really adding the total together and you're going to get your total. So in this case, vector addition is commutative. It is commutative. Remember that term from algebra. Commutative means it doesn't matter what order you add in. Does not matter what order you add in. It is going to be commutative. So adding vectors graphically. Now in this situation, this guy is walking multiple directions. You'll notice that he is walking north, 5.1 kilometers north, and then he goes 6.7 kilometers west. It's really nice when they have a north and west and whatever, because then we have this perfect right triangle. But what happens here is a little bit different. The resultant vector now is no longer just adding the two. We can't just add the 5.1 and the 6.7. That's the distance he traveled, but that's not his resultant. That's not what we think of as his displacement. What happens here is, and we talked about these terms, it's going to stretch from the tail of the first vector all the way to the tip of the last vector, or the head of the last vector. So we have this tail, that's my starting, to the head, or you'll see it called the tip here. So that's what my resultant will now look like when we have multiple directions. And you'll notice that it says when they are not identical, then you are not going to just have this addition, all right? When the directions are not identical, you're not just going to be able to add. If I was walking in a straight line and I stopped and then walked some more, I could just add and I would find my total displacement. But that's not true of when you change directions, all right? If the directions are not the same, you're not just going to be able to add those up. You can clearly see, just what you know about math, that I can't just add these two to get this guy. In fact, there's a pretty famous theorem that tells me what I do with that particular situation, right? So that's what's going to happen with your vectors. You're not just going to be able to add them, all right? So then what happens when we do this? So the direction of my resultant is actually going to be different if my directions were not identical. The directions are going to be different here. So here's what you find out. We're going to use the basic premise, and we'll get to this when we do our review of trig. But my direction was just north. This is what I was doing here. I was going directly north. And then I took a hard left and went directly west, right? However, this, you'll see, is a degree measurement. What I would say is I ended up 52.7 degrees west of north. Does everybody see that? I ended up 52.7 degrees west of north. If I wanted, Cartesian, if I wanted to do a Cartesian, then you're talking about what would it look like if I just drew this x-axis right here. Cartesian's going to be that measurement there, right? If I needed to use that, I would use a reference angle. And I would say, oh, what do I have left over, right? What do I have left over? And so all of these things are going to come into play when we start calculating things. At this point, we're not calculating the degrees. We will use trig to calculate those degrees if we know that information. But what you need to know is while he went due north and due west, he didn't end up either one of those. He actually ended up a combination of the two, which makes sense, right? It makes sense. That's why it would be a combination. And so you can't just add them. You can't just assume same direction, because that's not what happens in most of these problems. All right, so steps to adding them. First thing we're going to do is graphically, and then we're going to get to the algebraic, the trig piece of it. So the first thing you want to do is you want to choose a coordinate system. What we're going to use is we're going to use Cartesian for just the graphical ones. And then as we move to even our vector movement, when we do algebraic, we're going to throw it onto a Cartesian using what we know. So choose your coordinate system, appropriate scale. We're going to draw the given vectors. So the first thing you're going to do is you're going to draw your first vector, your first movement. And since we're going to be doing it on a Cartesian plane, you're going to start at the origin. What is the origin? What do I mean by origin? So if you're on a Cartesian plane, your origin is going to be 0, 0. From there, you're going to draw your subsequent. Subsequent means your following vectors, the ones that are behind it, starting from the tip of the previous vector. So we're going to start as we go. We're going to draw the next one from the arrow of that one forward or wherever it goes. And you're going to see this as we draw them. All right, so figure out what system you're on, draw from the origin, and draw each one from the tip. So the next thing we're going to do is we're going to draw the resultant from the tail of the first vector to the tip of the last vector. All right, and so while we had a nice pretty right triangle in that first example, you may not always have a right triangle. You will then measure the magnitude, that is the length, and the direction of the resultant vector. The length and the direction of the resultant vector. All right, so look at the example that they have given us. Look at your first example there. Bottom of the second page. A golfer is attempting to sink a putt. On his first putt, the ball rolls 11.3 meters at 10 degrees north of east. He putts again, the ball rolls 4.2 meters east, moving past the hole. His third putt is 1.7 meters at 43 degrees west of south. He sinks the ball. What was the resultant of his 3 putts? And so they've given you putt 1, putt 2, and putt 3. All right, and I've already given you your drawing there as well. So if you look at what happened here, his first putt, 11.3, and you'll say 10 degrees north of east. So that's how we drew this. This is my east, that's north of east. There we go. And then he went straight west from there. So you'll see that we started at the right here at the arrow, and we went straight west. That's just a horizontal movement, right? Or sorry, straight east, horizontal movement. And then it says 43 degrees west of south. So here's my south from that point. 43 degrees is this little guy right here. That's 43 degrees west of south. And he did that for 1.7. And so that's where his ball ended up, hopefully in the hole, right? If he ended up sinking it. So what they're telling us is to figure this out, we are going to go from his original putt straight to the hole. What would that have been? And so we're going to do this a couple of times, but as we see this movement, we're going to use, our first way of doing it is graphically. Our second way is going to use trig. But that's what we're ending up trying to figure out. What was it directly from his original putt to the hole? What would that look like? And that's what all of these problems are going to look like. Either what should it have been or where are they now based on the movement from beginning to end. All right? And we'll do some of these. When we start doing the examples, it'll make sense. So adding equal vectors, adding equal vectors. When you add a vector to itself, it's just like it sounds. It's just 2 times that vector. Because if you add a vector to itself, it's in the same direction. When you multiply a vector by a scalar, if it's positive, then its length or its magnitude will change, but its direction will stay the same. All right, so remember, scalar means just to multiply through. If it is positive, you're just going to increase the length by whatever that scalar was. However, when the scalar is negative, what happens is it goes in the opposite direction. So think about when you're multiplying by a negative just on the number line, right? When you're multiplying by a negative on the number line, it flip-flops to the other direction. That's what happens with negatives. That's what happens with vectors as well. When you multiply by a negative, whatever direction it was going, it just reverses and it's the opposite direction for that vector when you multiply by a negative. All right, so they show you some examples. This is my first vector here. If I multiply by 2, you see it stayed in the same direction. If I multiplied by a -1, it's the same length, but it went the opposite direction. When I multiplied by -1/2, opposite direction, and it cut it in half. All right, so that's what's happening with vectors, because remember, vectors are twofold. They're not just length, they're also direction. All right, so it's not just the length of it that you're worried about. Remember, that negative is actually just telling you direction for that vector. And so the direction is changing. So then vector subtraction is just like it sounds. It's adding the opposite. All right? So vectors can work against each other. Think about when you've done word problems in algebra with like the wind working with you and working against you, okay? So remember those distance, rate, and time problems with airplanes, and it would say, when you're going with the wind, what did you do with those rates? Well, you took the airplane rate and you added the wind rate. Why? Because the wind was helping you, right? But if you're going against the wind, it's like it's a negative vector. That's exactly what it is. You have an airplane going this way, you have wind working against it, pushing it that way, and that is why you're subtracting those rates, because you have one vector working against another one, because they're going opposite directions. And so that's what happens when we start adding these. You have to consider the movement of it, because wind or whatever is going to affect how something is moving. Current is going to push a boat, right? If a boat is traveling in still water, it's not going to be shifting left or right as it moves. If it's traveling in a strong current, you have to account for it, and you're actually going to be moving further off of your path, right? Because you have vectors pushing each other. So vector subtraction is not commutative, just like all subtraction, right? Anytime we add numbers, we can add in whatever order, but when we subtract, it's vitally important that we subtract in the order that we're given, all right? Because just like all numbers, subtraction is never commutative. So a pilot flew his plane with an airspeed velocity, vector A, 800 kilometers per hour at 37 degrees west of north. The wind was blowing so that the resultant ground speed was 700 kilometers per hour at 52 degrees west of north. What was the magnitude and direction of the wind? So again, these are going to be more like what we're going to do when we start throwing in trig. But if I were to draw this, you'll notice the first thing they give us is how the airplane is moving. The airplane is moving 800 kilometers per hour at 37 degrees west of north. So here's my north, right? And we'll actually be drawing these with your X and Y axis showing. West of north, that's what this 37 degrees is. And then the 800 represents the length or magnitude of that direction, the length or magnitude of that direction. Then we have wind blowing. Now we don't know the wind, so there's my wind right there. But we know that his actual movement looked 52 degrees west of north. So that's this one right here. Here's my north, west of north. And he was only going 700 there. And so what we'll be doing is we'll be using trig, and we'll be calculating what's going on to figure out what that wind is. What was the wind actually doing to push it that way? All right. So one more, and then we're going to do our little handout and get on the computers. Vector addition is the process by which vectors can be added. Vector addition accounts for both the magnitude, which is what we can think of as length, and the direction, which is going to be your degrees. Length and your direction. Length and direction. So now that I've calculated my overall resultant and I have this right triangle, how then do I figure out the length of my resultant? What theorem do you think I'm going to use here to figure out the length? Yes, I am going to use the Pythagorean theorem. I'm going to say a squared plus b squared equals my resultant. All right? So it actually doesn't matter to figure out the length or the magnitude of your resultant. The positive negative is not going to matter because it's actually going to work itself out in the square. All right, when we do the position in the next section, the positive negative will matter. But right now, to figure out the length of my resultant, which is that first question under the box that you see there on your page, it says magnitude of R, Pythagorean theorem. That's why it says that. To calculate your magnitude, you're going to say 11 squared plus 4 squared, and you're going to take that square root. So use your calculators. Calculate the square root of 11 squared plus 4 squared. So what do you get for the magnitude here? 0.7. 11.7. I want you to see is that beside that you see a little graph. You can use the computer, you can use the little program just because it's easy to click and drag, but you could also do this with just a piece of graph paper. right? You don't need a program to do this. I could take my pencil here and I could draw this on a piece of graph. I could draw this next one on my graph. I could draw this one on my graph, and then I could figure out what my resultant was, right? And I could do that just on the graph paper. So you can see that the little graph that they gave you beside it, you could do the same thing. You can actually sketch it yourself and put those together and figure out what your resultant was. You can also see you don't even have to graph it at all if you know the movement, right? If I know what my left and right movement is and my north and south movement, I can use that chart and calculate my overall movement. And then that's going to give me my horizontal, A, my vertical, B, and I can use A squared plus B squared equals C squared to calculate my resultant movement. Right now, we're just concentrating on length. We're going to add in our movement degree-wise in the next section. So what I want you to do is I want you to finish this sheet. The back sheet has several.